Okay, I'm going to cover probably like chapter 1 of the geometry book. It's fairly basic stuff so far, so I'll cover it pretty quickly. If you need me to go more in depth on something, just let me know and I'll explain it a little bit better. But I'm running through it kind of quick because it's mostly just basic stuff. In geometry, you have two types of symmetry. You have reflectional and rotational symmetry. Reflectional symmetry is the most common one. You see it every day, like a square. You have a line of symmetry right there, like where if you fold that in half, it's going to be the same either way. Same with if you had one facing that way, or if you had one this way. You can have a line of symmetry for reflectional symmetry. You can have a line of symmetry going in any direction as long as it's linear. So any linear function can be a line of symmetry as long as both sides are identical. One of the most common ones that you see all the time are faces. Human bodies and faces, for the most part, are symmetrical, which is why humans have such a favoritism towards, that's why they favor symmetrical things. Rotational symmetry is when if I have a square and I rotate it clockwise 90 degrees, it's going to look just like a square. Same if I rotate it 180 degrees or 270 degrees or 360 degrees. It's always going to look like a square. Because that's called four-way rotational symmetry, because it has four sides and I can rotate it four different ways. If you have something that looks like a star, well, if you have a star, I mean, I'm going to say this is a regular star. It's not because I can't draw, but this is a regular star, and all the sides and angles are how they should be. But this isn't a good example because it doesn't look right. But in a regular star, if you rotate it clockwise 72 degrees, it's going to look exactly the same. I'm getting that figure because, see, here's 1, 2, 3, 4, 5. 5 different points. Divide 360 by 5 because it's five-way rotational symmetry. You're going to get your 72. Also, if you rotate it 144 degrees, 216, 288, and 360 degrees, it's always going to look just like a star. Notice there's 5 of these because it's five-way rotational symmetry. Also, you're probably familiar with this from algebra. You have the midpoint formula, which is x1 plus x2 over 2 and y1 plus y2 over 2. Also, you can think of it as the average of the x's and the average of the y's. So if I have a line segment, say 1, 1 and 4, 4. These points, point 1, 1, point 4, 4. If I want to find the midpoint of that, I'll use this formula, or more simply take the averages of these two. The average of that is 5 halves, and 5 halves again. So the point 5 halves is exactly the midpoint of that line segment. There's some angles you're probably familiar with from other stuff, but there's a couple you're probably not. You have your right angle, which is 90 degrees. If you see something that looks like a right angle, you can never assume it's a right angle. You can only assume it's a right angle if it has that box on it to show that it is a 90-degree angle. Even if I had something that looks like that and I had that box, you know that's a 90-degree angle, even though it doesn't look like it. An acute angle is anything less than 90 degrees. An obtuse angle is anything more than 90 degrees, but less than 180 degrees. Something you're probably a little less familiar with, vertical angles, which is when if you have two intersecting lines like this, the two angles opposite each other are always going to be exactly the same. So if I have A, B, C, and D, A and C are opposite, they're always going to be congruent. They're always going to be the same. And B and D will always also be the same because they are opposite each other, vertical angles. You also have linear angles. This is also when you have two intersecting lines. So A, B, C, and D. The two adjacent sides, these two, see, these are opposites. Two adjacent angles are always going to equal 180 degrees. This makes sense because this is a line and has 180 degrees. It's divided in two parts. So the sum has to be 180. That does not mean that each one has to equal 90, but it does mean they have to total 180. you have complementary lines, or angles I mean. The sum is always going to be 90 degrees. For example, if I have this and that, and I told you they're complementary, you know that this plus this will equal 90 degrees. You also have supplementary angles, which are pretty much the same, except you know that that plus that equals 180 degrees. You know the two angles total 180. For example, on linear angles, C and D are supplementary angles because this plus this will always equal 180 degrees. There's also a term called concavity, which you may or may not be familiar with. A figure is always either convex or concave. If you have a figure like any of the regular figures, you know, like a regular hexagon, regular pentagon, those are always convex. And all of the angles point outwards. See that? They always point away. In a concave figure, one or more of the sides, or one or more angles, is pointing inwards, forming a cave, hence the name. So that's a concave figure, one you see all the time that I cannot draw. Well, I guess you don't see it all the time, but I can't draw it. These are all supposed to be straight lines, like a star. You have angles pointing in and some pointing out. That makes it concave because they have at least one cave. Some markings you see quite a bit in geometry. If two lines are parallel, you have them marked with a triangle. If they don't have a triangle, you cannot assume that they are parallel because maybe they have just a very small slope and they might actually intersect somewhere. Also, as I said earlier, 90 degrees, if it does not have the box, do not assume 90 degrees. If two angles are congruent, they'll have this marking. So anytime you see that marking, you know these two angles are exactly the same. If you see two line segments and you see this mark, you know that they're congruent. So you know they're exactly the same size and shape. Arc. When 2 points on a circle are connected through a line on that circle, it's called arc. A-R-C, not like Noah's Ark. See, it looks like giving this dude earmuffs. See? Earmuff man. That's an arc, right there. If I have this point labeled A and this B, that arc is called AB with a curved line over it. If it was a line segment going straight through, you would call it AB with a straight line, because line segment, arc. Alright, so if these two endpoints, we call them endpoints just like they're endpoints on a line segment, if these two endpoints happen to also be the endpoints of the diameter of the circle, this is called a semicircle. If the endpoints are closer together than that, and it's smaller than a semicircle, it's called a minor arc. And if they're farther apart than that, and it's bigger than a semicircle, it's called a major arc. It's kind of confusing because if I have a shape that looks like this, well, a circle, it looks like that, and I have these two endpoints, you don't know if I say arc AB, you don't know if I'm talking about this arc or this arc. So the only way for you to really know is if I specified major arc AB, then you know it's this one because it's bigger. If I said minor arc AB, you know it's the smaller one. Also, another way to say it is if I had another point here, point C, and I would say arc ACB, ACB, this arc. That's another way to know. What?
Look at the base.
A circle can have a chord. Anytime you have a straight line connecting 2 points on a circle, it's called a chord. The longest circle in the chord, or longest chord of a circle, is the diameter. Diameter is always the 2 points farthest away in a chord. A tangent point is when it just touches it, or as Riley says, it brushes the circle. If you draw a line from the center of the circle to the line of tangency, there will always be a 90-degree angle right there. You don't really need to know that for now, but you will need it for later. If you have
Faster.
If you have the game of... Oh, never mind. I guess I don't have time to say that. Yeah.